So now let's do the shear and moment diagrams for this situation. Now this one's a little bit different. We have a distributed load across the entire beam. And so remember from statics and mechanics class, a distributed load can be represented by a concentrated load that is placed where the centroid of the shape would be. So in this one's pretty easy because it's a box load. So the centroid will be right in the middle. So the concentrated load is just going to be our distributed load of 5 kilonewtons per meter times 6 meters. And so that'll be, 30 kilonewtons. But let's go through our steps. So step 1, draw a free body diagram and solve for the external forces. So as I look at this, I'm going to have a reaction at A. I'm going to have a reaction at B, and then I'm going to have the concentrated load. So the concentrated load is W times the length. So that would be our 5 kilonewton meters per meter times the meter, which would be 6 meters. And so now we need to solve for RA and RB. How do we do that? We go through our normal sum of the forces in the y direction equals 0, downward is positive, and so WL minus RA minus RB, that all equals 0, so RA equals RB. So now we'll do the sum of the moments about an end, we'll sum them around B, sum of the moments around point B, counterclockwise, that has to equal 0, and so what we have is RA times L, that's the entire length to there, and that's going to be going in a clockwise direction, so that's minus, plus WL times, well, this distance is L over 2. And all of that has to equal 0. So if we move RA over to the other side and divide through by L, what we're going to get is we'll get WL over 2. So our reaction forces are WL over 2. Both RA and RB are WL over 2, and they're both acting in the upwards direction. Okay, so that gets us there. The next thing we need to do is identify where each force starts and stops, and where each concentrated load is applied. And that's basically, it's going to start here and end here. This is a concentrated load, but the actual loading is a distributed load, which is going to start at A and end at B. So we really only have one zone that we have to look at because we do not have multiple zones in this part. So we're going to draw a free body diagram of any place that we cut in here because it's all going to do the same. And so if I cut a free body diagram there, and then I have my external force WL over 2, I have it, well here, let's finish out with the rest of our stuff first. We're going to have an internal shear and internal moment. So what I have from this point to this point is I still have a distributed load on top of that. So what do? Well, I replace that with a concentrated load. So the concentrated load, since it is a rectangular load, will be in the middle. It has a concentrated load, will be the intensity of the load, W, times the length. And so remember, this length here is x, because this is how far we're going in the cut. So Wx. And then, so what's the distance from here to here? Well, it's in the middle of it, and if this entire thing, to wherever we're looking, is x, well, the distance that this guy is looking at is x over 2. And from there, we can do our sum of our y forces, sum of our moments. So the sum of the y forces, downward is going to be positive, equals 0. So that's Wx minus WL over 2 will end up equaling to 0. Oh, cannot forget the shear force plus the shear force, because that's what we're trying to solve. So if we move the shear force to the other side, and if we collapse this down a little bit, what we'll have is W L over 2 minus x. So here's our shear equation. It's a linear equation with a negative slope. So now we'll do our moments. Sum of the moments about the end Counterclockwise is positive. That has to equal 0. So we'll start with, we have that screen switching noise. We have the moment. It's in counterclockwise. It's fine. Let's go to the reaction force, which will be a negative rotation, WL/2. So that is the amount of force times the distance, which is going to be x. And then we have this guy here, which is going to be going in a positive direction. And so it is Wx times its distance, x/2. And so now we can put all that stuff together. We can move all the W's to the other side. And then we can also make that a little bit cleaner too. So what we'll end up with is W/2 L times x minus x squared. As you can see, if we move these to the other side, positive, negative, we pull out the W/2 out of both of them, you're left with L times x and x squared. So there is our moment equation. So now we have another interesting equation. So this is a quadratic equation, so x squared x. So we're going to end up with a parabolic shape. So let's move on to the next step. So we now have our two equations. Let's move on to actually drawing the shear and the moment diagram. So up here is my distributed load that goes across the entire thing. My reaction. So I'm going to draw lines down at the beginning and the end. I have no dotted lines in the middle because it's going to be the entire same. There is my shear, and there is my moment. And let's just pull these from the other screen. So my shear is going to be WL/2 minus x. I'll leave some space. My moment is going to be W/2 LX minus x squared. Okay. First thing that we need to do is let's do the shear force and figure out where our two points are. So at x equals 0, that'll be the start. If I plug in 0 there, my shear force is going to be WL/2. Nice and easy. If I plug in L, then I'll have L/2 minus L, which will give me negative L/2. Then my shear force is WL/2, but negative. Now I know this is a linear equation, and it's a negative slope, so I know that these 2 points are going to connect. I'm kind of curious, where is it going to cross the axis? So where is V going to be 0? This will help me sketch it out. So at V equals 0, so if I plug in 0 here and solve this equation, I will find that x is L/2. So if that's 0, the only way that's going to be 0 is this side's got to be 0. W can't be 0, so we can divide through by that and it goes away. And the only way to make L/2 minus x 0 is to make it at L/2, which we'll say is right there. And then we draw a straight line. And that's our shear diagram. Okay, so the moment's a little bit wonkier, but let's figure out where it is at x equals 0. So x equals 0, this all becomes 0, so it starts at 0. Great. Moment is equal to 0. At x equals L, well, L times L is L squared. Minus L squared is 0, so moment is 0. And I know it's a parabolic shape, but I need to figure out where the maximum shear force is. Sorry, the maximum moment is. So, if you remember from mechanics statics class, the maximum moment is going to appear when the shear is 0. So it's basically what we're looking at is, because dm dx, as we derivate the moment with respect to x, that's what gives us our shear force. And so we know from calculus that your maxima and minima are going to appear when the slope is 0. And since this is the slope of the shear, well, we want that when that's 0. But we don't have to do any calculus because we know where the shear force is 0. We know the shear force is 0 at L/2. So I'm going to plug in at x is equal to L/2. Excuse me. So I'm just going to do a moment is W/2 L times L/2 minus L/2 squared. And so and that's the max moment. And so if I collapse this down a little bit, put everything together, what I'll get is WL squared over 2. Okay, and so that's our maximum moment. And that's not over 2, over 8. That's our maximum moment. It is positive, so we're going to come here and go WL squared over 8. And that's going to happen right here at L/2. And it's a parabolic shape. I'm going to sketch that in, and then there is my my moment diagram. Now notice I didn't plug in, we know W, we know L. We could plug all that in. I'm not so much concerned with that. I'm more concerned with being able to put these together. But I mean, I'm sure that you can go in and put in 5 kilonewtons per meter, multiply it by 6 squared, divided by 8, and actually have a number, which would be completely fine. Either of these are completely fine. I've just given the more general form.